Okay. Okay. Thank you everyone for coming. It is my pleasure to introduce the fourth speaker of four in this academic year in our series on explaining emerging technologies. This is Professor Rama Chellappa of the University of Maryland. He has a long and distinguished career in various aspects of machine learning and computer vision, and we are going to be treated to a very much inside baseball kind of talk about developing these applications. So the art of putting together effective applications, and how to understand the contents of these applications, not just telling us what he's been able to do with them. So let us thank our fourth speaker.
Can you hear me? Mic is working? Okay, thank you. Good afternoon. It's been a pleasure visiting the University of Buffalo. I've been here a few times. Of course, Niagara Falls is always an attraction. Came to Niagara Falls in 1979 when I was a graduate student at the University of Maryland. Since then, I have visited this university a few times. I have a lot of friends here. So, you know, when you give a talk in front of your friends, you have to be even more careful. They say, what Rama, what happened? You know, you used to give better talks than this before. So I'm feeling a little bit pressured, but we'll see how it goes. Anyway, I have the title, because everybody is with deep learning these days. Anybody doing shallow learning anymore? Not deep learning, right?
I am.
Learning?
I'm shallow.
Learning. That's good. That's good too, right? That's what we used to do. Not that learning was shallow, we were just doing shallow learning. Right, so since 2012, of course, deep learning has taken over. So the interesting thing that's going on now is, looks like when we have theory, it doesn't work well. When it works well, we're not able to explain it in theory. So I thought I'd present both, give a history of how we have used shallow and deep features for unsupervised domain adaptation, which is a very classical pattern recognition problem. So feel free to interrupt me. I've been a professor for 37 years, and I've read all kinds of evaluations of my teaching, so nothing worries me anymore. So you can ask me any questions you want, right? So what is domain adaptation? Well, in pattern recognition, we have a training data set, and we fit various models to it. If you have a parametric model, mixture of Gaussians and all that stuff. And then you build this machine, and then you send it over someplace, and hopefully the person will have data that is somewhat similar to what you have trained your machines on, right? Not exactly the same data, but at least hopefully it will come from the same distribution that you have assumed if you design the Bayesian classifier, for example. But it's not always true. It's, at least in computer vision, you know, we have variations due to elimination, pose, and all that stuff. So it's very likely that the test data comes from a different distribution. So how do you scale your approach? So a couple of ways to think about it. So you call training and test. We call it source and target. Source is the one where the data has labels, and target. Some of the samples in the target space may have labels, and some may, many may not. So even if you have some, then we call it semi-supervised, because we can understand the domain shift that has occurred and bootstrap from there. But if it turns out that all the samples in the target domain are not labeled, then it's totally unsupervised. So that's the first thing. And this particular thing assumes that both source and the target data are available, so that you can mediate, the domain shift, right? Oftentimes we may not know anything about target data. All we have is hopefully lots of source data. And we assume that the source data itself will be split into multiple domains. If you have a lot of data, that's possible. Even classical minimum distance classifier, we used to assume there are multiple templates that can characterize each class, right? So if you have that, then we can start thinking about domain generalization, just getting ready for the totally unknown thing. And that's a much harder problem. Right? So I'll briefly mention that. So the title was Shallow and Deep Features. So I'm going to talk about manifolds, which are kind of geometrically motivated representations, subspace representations, and then if you know, dictionaries became popular in 2009 thanks to the paper on SRC, classifier from Berkeley. So we have looked at it and how to adapt them, and of course you have to work on deep networks and so on. And then we'll discuss some open issues. Well, people tell me, sir, why do you still talk about shallow features? Aren't you happy with the performance you get with deep networks? I said, well, who knows? Deep networks may not do well. And sometimes you have to have a backup. And that's where the shallow features are useful. And also, the big thing these days is how to explain what happens inside of, on one layer network, right, with nonlinearities and so forth. So almost like, we have something that it's not clear to me what is more embarrassing. Not being able to explain why something doesn't work or why something works. What is more difficult?
Yeah.
It works, but we can't explain why it works. If it doesn't work, then we say, well, we don't know. There are other factors that we have not understood, right? So that bothers people. Anyway, so this is just basically setting it up. Now, if you think about unsupervised, suppose I have, all of your pictures, faces. I still want to build a face matcher. But I don't know who you are. Right? I don't have your labels. What is the best approach you can use for this problem? Principal component analysis, right? We don't care for your labels. We just take all your faces, align them, compute the covariance matrix, decide to keep 100, 200 eigenvalues, vectors, construct your eigenbases. Then I can take every one of your face and project it onto that and have your coefficients. And then I can ask, are these two people the same? I can do verification. I just have to project onto the eigen. So although principal component analysis is often considered, the least because it doesn't use labels and so on, it has a generalization property that's unsupervised, right? If you want to do SVM or LDA, you need to know the class table. So that's one of the things that occurred to us, that if you have unsupervised domain adaptation problem, where I have source labels but no target labels, then I have to get into the PCA thing. So I have all of these guys here, all of these guys over there. I can compute the subspace representations and put it on something that's known as manifolds. Okay, fine. We were motivated by the ECCV 2010 paper that came from Berkeley, Trevor Dar's group, Keksenko. We had known that this problem existed. Like even for a simple iris sensor, if you take two sensors, manufactured by the same company, LG, you design your algorithm using the first sensor and you test it on the second one, the numbers go down. So this is known. So here what they did was they took pictures of simple objects that you often find in office, called office data set, 3 different kinds of cameras, webcam, DSLR, Amazon, and they found drop in performance when they went from one to the other. So we have a paper in PAMI to address it in the context of iris sensors, on the sensor adaptation, and so forth. So we were kind of aware of this problem. So when this data set came, we said, okay, let's try it. And then my student said, well, they did the semi-supervised, so I want to, by the way, this is the thing, domain adaptation, transfer learning. There's some subtle differences in terms of the assumptions, marginals, conditionals, so it's okay. Let's not worry about that. So, all right, so when you do this, you can project them onto the orthonormal matrices, right? So this Grassmannian manifold is one such representation, somewhat related to Steffel manifolds and so forth. So this is the idea. Idea is I have all the labels, source, I'm putting it there, all the targets, I'm putting there. I know the labels here, I don't know the labels, and I'd like to interpolate. So if they both lie on this manifold, there are well-defined equations that will take you and connect them, okay? And so for at each one of those intermediate points, I will have the subspace structure, and then I can take these two guys, project onto that, and generate a very long feature vector, and then I use that as a way to classify. That's a very simple idea. unsupervised method. So the catch here is that understanding for unsupervised through PCA and then interpolate between them. You can view this as being equivalent to having at these intermediate points lots of data, because then I can do PCA at the source, PCA at the target, PCA at the every intermediate point, and then it's like having eigenimages corresponding to multiple poses, multiple elimination conditions. Assuming if they correspond to your shift, then you can take your two data and project on them. You have a pretty long vector, right? If it is a lot of intermediate points, then you can do some partial least squares and things like that. So these are standard things. So those are details, but the first thing to realize is to develop this interpolation, because later on we will show similar things using dictionaries. So the idea is to mediate between the domain shift, right? Now, there's how do you do this? There are some standard equations. I can show you. You can make the time t go not time. It's a variable t, 0 to 1, so you can continuously. When we first did this for ICCV 2011, I told my student the paper won't get accepted, because some of the numbers we had like 30%, 40%. Of course, ICCVs, ECCVs, CDPR, they want 92, 93, like that, So I know I'm being recorded, but I'm going to make some statements. Over the years now, CVPR has become kind of a numbers conference. Oftentimes I'm hearing young professors saying, oh, let's just download that code and hack it up and get some 2% up and then submit. It's somewhat discomforting, but that's where we are right now. The good old days in image processing, image compression, we used to joke if you have a 1 dB improvement in PSNR, peak signal to noise ratio, then it's a conference paper. 2 dB and above is a great journal paper. 5 dB you get an award, technical achievement award, where that scale. So there was a numbers-driven improvement because PSNR was measured. So here, I'm thinking of writing a software for accepting CVPR papers. I'm going to look at the last 2 entries in the last table of the paper, and I'm going to say the numbers are better than 2% accept as a poster and so on. It's somewhat sad, because so when we are area chairs, we actually tell the reviewers, please don't look at the numbers, look at the ideas too. Sometimes the ideas are great, they're not fully developed. If you work with them, they'll get better. So this was like 30%. I'll show you the numbers. I told my student, no, don't bother. I know you want to go to Barcelona, but this is not the approach. But most students of mine don't listen to what I say. In fact, the successful ones they are successful because they never listen to me. I don't know, Professor, do you have the same problem? Yeah, the good ones don't listen to you. Yeah, so I said it's all right. Okay, so these are basic equations. You do a PCA for both source and target, S0, S1 and S2, and then you do some matrix completion things and so forth. These are all in our papers. The idea is we basically imagine we are doing PCA at many, many intermediate points in between source and target. That itself is, is a beginning thing, because the subspace things have issues with geometry, right? Illumination you can probably capture, but if there's a lot of pose variations, it's going to be difficult. But it's all right. Anyway, so, all right, so collection. And then we had this paper in the ICCV 2011, and Fei, Shah, Kristen Grumman, and Gong, who used to be at UCF, they came up with a slight modification, a couple of lines of change in code that produced better numbers, so that they were called the infinite intermediate subspaces and so on. It's a paper in CVPR 2012, and but then when you take source that has labels, target, and then you project them onto the multiple things, for each such point you get a PCA vector code, and you put them together. It's usually large, so you do partial least squares is a way of reducing dimensionality using label information from the thing. So look at the numbers. The Kopalan, that is the ICCV paper, 19%. This was an oral paper in ICC. I was shocked when we got the thing. I said, oh, unsupervised domain adaptation. Nobody has done it before, so we should let it go. And as you can see, from webcam to DSLR, we were 19. And this is, since then, a lot of people have extended that. So DSLR to webcam, 26%, 39%. So to all the young folks, if you have a great idea, just submit it. It's okay. There are at least some reviewers in some area chairs who will appreciate the novelty of the work. And so don't try to hack to get to our 90s. You know, it's not necessary. It's encouraging, right? And then she and Shah is, Shah is again at USC. So we tried all kinds of things, various assumptions in terms of how much you know, how much you know about the labels and so on. So in general, it was like this, and then we said let's assume semi-supervised, because then we can compare with Senko, right? She had a semi-supervised model, so she was 27 and we were 37, and so on. And as you can see, the numbers were fine, although the performance was lower than what you would expect. So, and then we said, what if we divide into multiple domains and so forth, does it help? This is like having multiple templates for each class, right? So this is useful later on for domain generalization, okay? So, all right, so basically we tried a method that's good for unsupervised domain adaptation, okay? This is getting worked on, but more and more people have moved away from these kinds of approaches because deep learning performance, as I'm going to show you, a few, 20 minutes, maybe 10 minutes from now, is pretty good. So that's a problem we face. Anyway, and then we had this nice work from Berkeley. If you remember SRC, right? This is from John Wright, Hema, Shankar Sastry, and Ganesh, I think. They were pretty impressed with the method that they developed. At that time, it was very good. It worked very well when you had black patches on your faces, occlusion, and so on. I'll briefly describe what that method about. But before that, some of us were looking at these dictionaries, representations for signals, hierarchical representations. And then there is this nice work that came from Olhausen and Field that instead of doing handcrafted things using wavelets and wavelet packets as suggested by Steve Malak, if you can learn dictionaries from data, so you can view this as one of the first examples of data-driven representations that kind of panned out. Right? Has neural basis and so on. So there are a couple of ways to learn dictionaries. KSVD is one that's mostly used, and I'm going to tell you in the next slide how the mathematics comes about. But again, anything that uses just the appearance has issues in terms of geometry. That's pose and all that. So suppose I take all of your faces. Let's assume I only have one face from each one of you. Or let's assume I have several from each one of you. So I can stack them all together and make this guy D. Or I can make them as Xij, right? I think I have so this one. So this says that I have a certain number of faces from certain number of people. This part of the training data set, and these are coefficients. This Y is the test guy. That's me. I'm not part of you. Okay, so I'm claiming I can write me as a linear combination of all of you. Now that would give Fukunaga, my professor who taught me pattern recognition, shivers. Because I'm a test sample, I'm writing it as a linear combination of training data set is not something he would appreciate. By the way, I studied at Purdue. I don't know how many of you have heard of Professor Fukunaga, not this group here. Anybody here has read book by him? Statistical Pattern Recognition. He wrote the first book, second book, 1972. Purdue had a great group of people at that time. Professor Patrick, who actually got an MD after he was done with this pattern recognition. He became a doctor and all that. His book was 1968, very statistically driven, and Fukunaga same way, Kingson Fu, and so on. So Professor Fukunaga's mantra was that what is good for representation need not be good for discrimination. So all these generative models are kind of going against his way of thinking. So he used to teach pattern recognition, and he would bring his book every fall, put it on the table, and write the whole book. He knew it by heart, every equation in the book. So if you just recorded his thing, it's like recording his book. Okay, fine. Now, see, anytime you bring in Professor 60 plus, they tell all these stories. Right? Y is me, and I'm writing it like that. Suppose if Y, I were there, one of you, for argument, then what happens? Most alphas are 0, only the alpha that corresponds to me is 1, because I'm actually one of the x's. So that means alpha is now a sparse vector. Okay? So I can try to get alpha using the L1 optimization approach, or L0 in theory. This is a nice thing. Everybody starts with, in the compressive sensing literature, we want to estimate, get a vector that has the fewest number of non-zero things, and then we say, wait a minute, it's a computer science building, so it gets into the NP issues, so we'll say, let's do it using L1. Then linear programming methods can be used for finding alpha. Suppose I get the alpha, but subject to that condition, right? Y is equal, that's my assumption. And then what I can do, since I have all of these D's, I can synthesize using the estimated alpha. And then I can find out the difference between the original Y and the estimated Y. Whichever gives the smallest distance, I pull the label from there and I assign the class label. You follow me? How this is how it was. I think when it first came, it was really very interesting. In fact, I even know that there were articles from Berkeley that said this is a breakthrough and so forth. But within 3 years, of course, deep network came and it broke everything. But at that time, this was pretty impressive, and they had issues in terms of alignment, how do you handle that, and so on. And we looked at the problem of how do you handle it when there is illumination change. See, dictionaries are still appearance things, and as you know in vision, if you change lighting, if you change, where you acquire the picture from and so on, it's all of these change. So we will take from these X's, we will build 3D models using shape from shading techniques, and then we'll build an expanded dictionary that will account for various illumination variations, post variations, and so forth. So this is how you build your dictionary. It's called KSVD. It's one of the most cited papers in the dictionary world, Michael Ellard and Brookstein and so on. So it goes back and forth between a sparse coding method and a dictionary updating method. Actually, it was a conference, and I think there's a journal version. Anyway, so this is something we played with, but they were not really domain adaptive, right? So we had to come up with domain adaptive methods for a dictionary. That was our religion for a while. So we said, how do you do it? You can take the source and the target domain and then project it onto a space where they kind of sit together, and then you try to figure out what the representation should be, and then you will use that for your test data set. So how does this work? Well, you can give matrices Y1 and Y2 from source and target, then learn a shared dictionary, and then just to make the math all worked out, you have to make some orthonormal conditions and so on to avoid some trivial conditions. And then you learn a representation that basically mediates the domain shift. I mean, that's the whole point again and again. Of course, these are mathematical derivations, they are papers, so I won't belabor much on that. Okay, so, and then you can also add additional things in terms of how to separate within class and between class and so on. There are always these parameters, mu's and no's. If you see all of the deep learning thing that's going on, or even in shallow learning, there are always these parameters that are hanging around, all right? So we have given them some respect by calling them, at least in the context of deep learning, which I'll discuss very quickly, hyperparameters, and the tuning is a big issue. So, that is one of the challenges with these methods. I'm sorry. Now look here. With these dictionaries, the performance has gotten better. Before, I used to be in the 20s and so on. So if you look at, this is somewhat similar to PayShop. GFK is an extension of our method, and there are various methods. We are already in the 46 and so forth, and this is the one that uses. So, going to 70s, from 30s and 40s was an improvement, right? When you have a single source, and with the C to A, C to D is, what here happened was we also added Caltech 101 data sets here to see if we can have a larger data set, because the Office data set was more smaller. So Amazon to Caltech, Amazon to webcam, webcam to Amazon, all possible. So this was a little bit encouraging. Okay, and then of course when you go to multiple things, we had some issues with dictionaries. Okay, so then my student said, can we really build something that is originally in the 1997 paper by fellows from Berkeley? So we thought we will mimic the structures, and at that time we were not aware of deep learning. I was not a big fan of challenges. All these challenges that happen, imagine a challenge, this challenge. Every CVPR you are challenged by 8 workshops, so forth. So I told my students, we have enough things to do, we don't want to be distracted. Okay, so I didn't pay attention to ImageNet. I heard that Pepe Lee was doing that. I said, wonderful, despite the fact everybody told her she should not do it. That's why I really like her work. She's a young assistant professor. People say, oh, you can't collect data and annotate them and get tenure. But for instance, she said, man, I'm going to do it. Okay, so that kind of changed, right? The ImageNet is the one that contributed to the new revolution. We had no idea. We were not paying any attention to it, but we thought we should probably come up with a structure, that somewhat talks about this. So we came with max pooling and all of that. And as Professor Shriari mentioned, I'm unnecessarily getting credit for max pooling. I don't know. I bought this book, Deep Learning book, right? This book, so I'm like a good student. I'm reading, and I'm reading, and I'm reading. It's a big book, so 330 page, I'm there. And there is a little thing on max pooling. I said, oh, okay, max pooling. And then I was shocked to see that their site, my paper was one of my students in 1988, max pooling. We didn't even call it max pooling. We called it something else in the context of building a neural network for stereo. Because if you are doing stereo, you have to have only one depth value for a physical point that cannot have multiple depth values. So we have to do max pooling. So then I said, okay, when my students graduate, I give them all like a gift, a book. I said, okay, that's the book I'm going to give them. And I put an yellow marker on page 330, and we discovered max pooling. I'm not sure. In fact, people don't like max pooling these days. There's two views on it. Some like, some don't. Anyway, so we built a machine like this. It's kind of not deep. It's not deep because it uses these kinds of mathematics. And so, cost function at each layer, and then you want to optimize it. At that time, we didn't have GPUs. We had no idea. This was 2012, 2013. So we kind of did with what you can call as shallow depth, 3, 4, so on. So basically, optimization to find out a representation, and then again the idea is to transform to a common feature space. But the only difference between the previous method is it's hierarchical, it had the pooling idea and all of that. Okay, so we did experiments for these kinds of data. Suppose you have, the Caltech data, you may have the RGB, or you may have the halftone, you may have the edges. Can you go back and forth among these various things? And we played with it. Well, numbers got better again with this one. This is from 10 common classes between Caltech and the Amazon cameras. And so this is 71, 81, 54, 68, and so forth. So we were kind of happy about it. Maybe if we had gone more deeper and deeper in terms of the hierarchy, this would have worked well. But at that time, it took too much time. So we published some papers and we moved on. And then we added more classes. So the performance was improving. So definitely the dictionaries were doing better than the manifolds we were considering before. For the simple reason, in the Grassmannian manifold, we were trying to generate too much from just 2 boundary points. When you look at it mathematically, the equations are fine. But if I had PCA equivalent description or samples corresponding to those, I could have regularized them better. So if you have just 2 pegs, and if you want to fill everything in between, it's going to be weak. But with dictionaries, it was possible because of the convolutional representations we had. Anyway, so we added more classes, and then published, and we were kind of happy. And then suddenly it turned to us, well, just like we did for the manifolds, can we also interpolate between dictionaries and see whether that would work. So this was a paper, the idea here was, let's get something that is common, and then let's get something specific for each. So you can see that this is somewhat like replicating the manifold approach. So we built a lot of intermediate dictionaries, and so first we have to initialize them, and there is a domain shifting term, domain adaptive term. So basically the idea is to get the common dictionary. It's almost like the trend, and then what are the bumps over the trend as you go from one point to the other point, right? So one can actually relate this to the manifold approach with a little bit of involved mathematics. Okay, so then you have to reconstruct the. All right, so get the features. Look at these numbers. They are various things. Of course, you have to see the last column here, and that it grows. Now I'm talking about 93. That looks like the CVPR number. Right? So 93 and 92 and so on. So the unsupervised domain adaptation at that time, these were the best numbers, and it kind of replicated the idea of manifolds but using sparse dictionaries. And then our world collapsed. Somebody said, sir, there are deep features. Okay, so we did deep features. And when you do deep features, look what happened here. 99.5, 48.4, 98. So some domain shifts are easier to work with compared to others. There's still some challenges, right? W to A, 48% is not great, but some are easier than others, okay? So this is when all of computer vision changed. I wish I had paid attention to image and challenge. Maybe then we would not have worked so hard to reach this. Okay, so then, as you know, AlexNet came, InceptionNet came. How many of you are not doing deep learning here again? I want to check. Have you? Okay, that's good. Must be a mathematician.
Yeah, originally.
Yeah, that's right. I can appreciate that. You still do deep and shallow. Yeah. You have to pay for the bills as well as do something for the soul. Yeah. Math is for the soul. Pay the bills is deep learning. Okay. So once this happened, we had to kind of think about how do we do domain adaptation using a deep learning framework. Well, luckily GANs came. GAN is, I come from the generative approach, right? We like to model everything. Markov random fields. That was my PhD thesis topic. I couldn't model more than 32 by 32 picture of a texture class, somewhat like this, micro textures and so on. Because they really couldn't model pictures. They could generate realistic pictures. Have you seen the faces that are generated by GANs now? I can't tell. In fact, in the DARPA program on Manifold, one of the tasks is, can you tell whether this face was acquired by a camera or by generated by a GAN? It's really that good, right?
Wow.
So as a generative model person, I'm not too unhappy about it, but come to think of it, everybody talks about deep learning. Should we call it deep learning or should we call it deep fitting?
Yeah.
What do you think? How many of you think it should be deep fitting? Don't be afraid, you can say that. Right? It's like a nonlinear hierarchical regression model. Except that the estimation procedures have no bearing in statistics. Right? When you have a linear regression model, what then you have? Least squares, maximum likelihood, Bayesian, you can put priors. None of that. It's just an optimization method, SGD. You don't know where it goes, but it looks like the numbers are good. So I'm not sure, well, it's okay. Now I've made my statement whether it should be deep learning or deep fitting. I'm on a slippery slope. I may just continue along that path. Why do we call deep learning AI? Have you looked at the table of contents of AI book by Russell and Norvig? There's one of the chapters probably neural networks, but all these issues about knowledge representation and hypothesis, blah, 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 blah. So now everything is AI. In fact, if you go to AI in medicine, SVM is AI, nearest neighbor rule is AI. That's what they think, regression is AI. I don't know. I think everybody is using AI a little loosely. And see, as people, we should all stand up and say what is AI and not AI, okay? That's just my 2 bits. Anyway, but this is a beautiful approach. I think if you have not, I don't think anybody here doesn't know what a GAN is, but please read the 2014 paper. It's really absolute delight to read. It starts on a nice footing. You know, the first few pages are like estimation theory, right? Likelihood and all of that. So I'm thinking, you know, Ian Goodfellow has done a wonderful job. And somebody told me that his GAN paper was cited 50,000 times last year, just 1 year, you know, in this world. But it's a nice paper and it's a very good idea. Basically, what does it say? I think its original motivation was to improve the number of training samples or something like that. So I have real samples and I like to generate more that look like it. So I start with a Gaussian vector and then I have a generator, which is a deep network of some sort. I generate, the discriminator looks at it and says, no, you are not as good as real samples, go away. And then this thing continues in, you know, in max scale and so on. Finally, when it converges, G is ready to synthesize things that look like real samples. Okay, there's a lot of work that's getting done now, but this has given rise to all kinds of issues, which we'll discuss a bit later. Deep fakes is becoming a big problem now.
Yeah.
You know, everybody wants to know. It's quite possible a few years from now, every data information knows that it can be generated by a GAN. You won't need me here 5 years from now. We'll just have a GAN talk like me and do the same lecture, right? So it's scary. Scary from security point of view and so forth. So how GANs and domain adaptation will work together? In GAN, the competition is between the Gaussian vector and the training data you have. In the domain adaptation, the competition is between source and target. So you can view, instead of the real data that you have in GAN, put the source there because you have the labels. And then the Gaussian thing, you put the target, and then you now will figure out a way to learn a feature embedding that kind of shares the characteristics of the source and the target. And that's again the simple idea, but it worked much better than we thought, right? So, you know, so this is, we have the 2 papers in CVPR 2018. So this is how it works. Now I have labels for the source. And this could be your general deep network, and then I have the classifier, and then this part is well understood, your standard training. And I have here the target samples, and I don't know the source. So they go through here, and this is the adversarial portion, right, where the source and the target come, and we have the generator network, and then the discriminator network decides whether it's from the source or the target. The difference here is I have multiple classes, so I need to not only decide between a source and the target, I also would like to synthesize things that look like you know, source. Basically, we want to look at the target and create samples from the target that look like source, because I know the labels for source. So in the manifold, I try to interpolate. In the dictionary, I try to interpolate. In the projection method, I try to put them all and make them live in the same house so that I can leverage that and classify. Now what I'm trying to do is I'm going to beat up the target so they look more and more like source, because I know the labels for the source, so I can, you know, do the classification. So this was the idea is finally when this one converges, you have the feature embedding that has the features of source and target, and then I will put it there and do the classification network. So when this one comes, the feature and the classifier network will work. Okay, so this is the approach, and then we have these kinds of things. 89. Before we had 90 and all that, now 72, 71, and so on. Right. So you look at the bottom numbers. Now the next one is the most revealing. When I did with manifolds 2012, I didn't have these numbers. I had these. Dictionaries got slightly better. And then I replaced sparse coding with deep features. Suddenly you look from here to here, from here to here, from here to here. This. And then now I do the GANs performance. So this is why everybody is crazy about deep networks and GANs, because the performance is good, for this problem. Now, we also do similar things for semantic segmentation. Semantic segmentation, you want to put a label on each pixel, you want to have a lot of training data. It takes time to ask people to put labels, to generate. Suppose what if I have synthetic data, but then I want to segment real data? Again, it's a domain adaptation problem. Synthetic to real. It's the most challenging domain adaptation problem. And so we have same setup as we have done, and you will see the interesting thing is, of course, you have these kinds of, this is standard experiments you have to do. This is the criteria for deciding whether segmentation is good. And these are the two synthetic data sets, this is the real data sets, and so on. And if you, this is the artificial data set, real data set, okay? The improvement is about 9.1% in terms of segmentation gain. That is good. What is more interesting is, look at that after certain iterations, right? It's not good. The GANs are not producing good. Oh, wait a minute. It should, something happened, because I'm supposed to show you very good results. Maybe that's showing the last one itself. Okay, yeah, that's right. I think, I don't know why the meetings, usually for every 5,000, 20,000, 40,000, I'll have, but do you see the quality? There's no way I had any model that can synthesize these kinds of pictures. So GANs are good, but we have to start analyzing them, why they are good. So we are working with one of our CS faculty members and trying to come up with likelihood bounds and so on for GAN-generated data, because after all, it's a distribution that starts with the Gaussian and so on, and to see if we can do inference with them. So that's something, we have a paper in ICML this year. Okay, now, so much for domain adaptation. Now I'm going to talk a little, how much time do I have?
Until, 3:30 or 4:30.
Okay, what's the time now? It's okay. I'll talk, take questions. Not good. So domain
4:15,
adaptation
yep.
was bothering us a little bit because it assumes everything I've said so far that both source and target are available. Now, what do you do with domain generalization? I have no idea of what the source is going to be, but then you can't really spin something from nothing. So what here we assume is, we assume the source is pretty broad. That means we can collect a lot of data. These days we can collect, continue to collect. So that means you will have enough diversity in your training data itself. Hopefully you can work with that. And then anything that comes out for the target, you are able to manage it. That's the only way to do, because how can you predict something that you don't see, right? So we basically, what is the basic principle, right? You need an intuition for everyone. If you are familiar with regularization approach to computer vision, we'll have two terms. One is the data term. For example, in from shading, you have the intensity image, and then you have the reflectance map, which is a nonlinear transformation of the depth, derivatives of depth and so on. You take the difference between them, square them, plus you have the regularization term. Optical flow, the same way. Now, the good old days, for these methods to converge, because of the nonlinearity of the reflectance map, and motion problem, and so on, the regularization parameter will be very high. Lambda, we have to keep it large. And so the familiar thing that we used to say in those days is that you got to keep it so large that you may be actually walking away from the data, because we emphasize so much on the smoothness and so forth. Now, if you turn the argument around for domain generalization, if you are not committed to any training data, then are you better off in terms of meeting the demands of a test data that you have not seen? So we thought we had to bring in some idea of regularization here, okay? Regularization, at the same time, not be too concerned. So the proposed approach, as I said, is based on the regularization, and then there's something learning to learn, it's called meta learning, and so forth. So this is a paper in Neurips last year. So this is what we do. We have many subset of networks. We assume that the training data is very diverse, very large, okay, large and very diverse. And then we can actually associate multiple domains, okay. Think of it, all frontal faces is a domain, side faces another domain. Somewhere in between 30 degrees is one domain, 40 degrees, something. So you have multiple domains, multiple elimination conditions like that, and you can now start designing for multiple each task, okay, multiple feature network across all source domains. And then you have each task network TI trained on source domain I, okay. So we have multiple networks, and then we take all the features out, and then we do a single network trained on all source domains. So what are the various loss functions that we have used? So there is the standard SGD path. This is the loss on domain I computed using TI, and then we have the cross entropy loss for source domain, and there is a regularization function which kind of tries to accommodate the fact that you can actually move away from the data term. Okay. So basically, we have n domains, so n into n minus 1 by 2. We train that many separate networks, and then we get the features, and then we keep with all the training data taken from all the domains, and again fine-tune them. So this is somewhat working, but not great yet. So we have these kinds of performance. Somewhere it is 4%. These are standard data sets that are available for doing this domain generalization problem. So as you can see, it's much harder than domain adaptation, because there we have many 90s, but here they're still in the 60s and so forth. And we have other kinds of tests we have to run. So sometimes you get reasonable. Here it is fine, not great, and so on. So this is an ongoing problem, an ongoing challenge, because we still are not sure how much to regularize and how much to go with the source domain and so on. Okay. So I'm going to kind of stop here and take questions. Domain adaptation is an old problem. We're still struggling with the data sets. You see CVPRs have a lot of papers on this. Neurips, CVPR, ICML, everywhere it's there now. So we contributed to the unsupervised version of it and talked about manifold, shallow features, and GANs. Of course, GANs are the best. And then, we have to see if we can go. One of the problems that everybody is talking to us, various governments, they have collected a lot of data. This is true even when everybody has lots of data, and they have very little annotation. Right? So they don't want to spend their high labor charges on putting labels. They can't send their data to Amazon Turkish. Definitely from hospital, there's all these privacy issues, and many government agency data is, classified and all that. So how do we start with some label data set and generalize to unsupervised label, right? So unsupervised domain adaptation will be there for a while, okay? So it's being bombarded, because people think graduate students are very inexpensive. Is that true? So, we can just send you this data, and we can have, now that you have done it for this, for that, maybe you should. I said, no, my graduate students are very expensive. The next year, they're going to be extremely expensive. So that problem is what we should be looking at. Now, in terms of all this interest about machine learning, AI, deep learning, etc., where is the future? I'm thinking about this. We have never seen something like this where one idea is sweeping everybody. I feel like I'm in the mid-60s when everybody did FFT because it was a cool thing to do. Cool, you took whether they needed it or not, you took FFT. don't know if we can kind of survive like this, when the whole universe is doing deep learning. It's very hard to tell the difference one from the other. And cannot be just all on the basis of experiments and ablation studies. So our vision field is going through some nasty times, I think. Although we like the fact a lot more people are coming to our conferences. When I did CVPR in 1989, I think that's where Venu had a paper on face detection, I thought. You know, we had 350 people. Nice conference. Now we have 6,000 people. Right? So it seems to me that while there is all this buzz about smart cars, autonomous cars, etc., I think AI or deep learning in medicine probably is something that may have some impact. Again, be careful what people call as AI. If you look at the literature like JAMA, Journal of American Medical Association, New England Medicine, the Journal of Medicine, and all of that, lot of low-hanging fruits are in taking AlexNet, VGGNet, and run through annotated diabetic retinopathy, or skin cancer, things like that. And sure, they're getting a great performance improvements, and they're all excited, right? We're also seeing things like logistic regression being used in OR data when somebody is under anesthesia. My son tells me his worry is whether they'll ever go to low blood pressure situation because it's very difficult to recover from that. So they want to have a prediction. As data comes streaming, being able to predict. So prediction is going to be a prediction of outcomes, as they call it, or undesirable outcomes. Okay, you guys have a medical school nearby. Okay. So I think all CS people should just go and talk to the doctors and see, because there's tremendous potential. There are so many different problems. Every organ has its own pathology, its own data set, its own issues. Okay, so definitely that's where the thing is. The second thing where I think everything is going to be is in securing these things. As you know, there are hundreds of examples where you change a few pixels, the baby becomes a monkey, and the monkey becomes a rifle, the rifle becomes an umbrella, and it's more annoying to a computer vision person. And I have to note that people who generate these examples are non-computer vision people. They are all excited by that. So what is the protection for it? So we have a paper called Defense GAN in ICLR last year in April. Again, it's a very heuristic idea. We use a GAN to generate, fit to the given data, and whenever an adversarial input comes, we try to smother it and make sure we find the closest input example to the given adversarial example. But then it won't cause harm, because it's good input will create good output. That's how we design the GAN. So it's like outlier detection and smothering it. Some of you may be aware of robust statistics, Tukey's redescending function, and so on, which is a way to smother the outliers and send it through the regression. Now, at ICLR, there were 7 papers that claimed robustness. And then at ICML, this is a few months later, Carlini-Wagner, he tried to shoot down all these 7 methods for the MNIST and fashion MNIST data. So the idea is build a GAN and then see if adversarial input comes, try to knock it. Because Carlini, you have the white attacks, the black attacks, and then the Carlini-Wagner attacks, right? So 6, the performance went down, 0, 20, 30, and ours survived, according to them, 55%. So my students complained. They said, no, it should be more than that. I said, no, don't fight over it, it's fine. So I told Carlini, thanks for attacking us. You broke our knees, but our heart is still pumping. So he said, Rama, I don't know if you were in my talk, I encourage everybody to beat your network. I said, what kind of thing is that? I'm trying to be a peaceful person. Why attack my network like that? They're still trying. Now we are able to also protect against CFAR, which is one of the computers. Because MNIST, FMNIST, mission people don't think it's a serious data. I mean, that's the way this is. You can complain about it or not, but they don't. Anyway, so CFAR is kind of an object recognition thing. So what is the problem with that is we are doing this piecemeal data on data. You can't do that, right? You should have a gentleman. So protecting deep networks against attacks is going to be a big issue, because suddenly if you are doing very well, then people want to attack you. There was an article in Washington Post some time ago, how people can get into the CT machine and then put fake cancer cells in your CT image. Or if there were really cancer cells, remove them. So to trick the doctors, it's a big thing. You know, so all of these are happening, and now Medifor is big on what to do with deep fakes. Everybody is so worried about that. This is a program that Professor Dave Dorman started. Actually, when Dave started, we all thought it's a very cute problem. We liked it, you know, because Hani Farid was working on it and so forth. But it is now the most visible program in DARPA. Hani Farid says he gets requests for interviews all the time because it's a very tough problem. Right? How do you figure out? Because doctoring can be done in multiple number of ways. Right? So those of you working in deep learning, there's lots of problems for you to look at. Don't run deep learning on standard data sets and so on. There are more problems. Adversarial thing, medicine. And missing thing for computer vision, incorporating geometry. Vision is all about geometry. And we don't have it yet. The sum atoms are being made. It's all based on how the training data is. It directly captures the variation geometry, but not explicitly. So there is some more deeper mathematics is needed. So with those comments, I wish you all very, very deep learning-based career. Thank you.
Okay. We have time for questions, so feel welcome to ask questions.
I need deep questions, no shallow questions.
Okay.
Rama, you gave a nice overview of what's happening in the field as well as the very interesting research on GANs. The area of computational linguistics, which is not what you're talking about, they are finding that many of the traditional methods they were using were all blown away by these machine learning, deep learning approaches. Saying there's no point in studying all these syntactical methods or whatever. You have been a close observer of the computer vision field, and there were, for a while, the big things used to be like optical flow, shape from X, and all that kind of thing. There is I've not been following closely the computer vision community, but is that what's happening because of all these developments in deep learning? There is less of this and almost all dominated by GANs and...
Actually, we use deep learning for estimating optical flow, I3D.
So they're just being used as tools for doing the same thing.
Exactly.
So it's not blown away the traditional areas.
And there is shape network from David Jacobs' group, which basically tries to implement shape from shading using deep network. See, deep network is, to me, nothing but a hierarchical regression machine. That's all it is. All these things, convolution is way. Just that we have lousy methods of parameter estimation according to a mathematical statistician. And it's a regression machine, with too many parameters, overfitting and all that stuff that goes with it. But no, we have optical flow. But you know where it's not working? In phase, it works beautifully because I have so much data. MS seller data, 10 million, I can curate it, bring it out to 6 million. We designed the best phase matcher as part of the IARPA Janus program. All university effort is being used in places that, and we never thought we could meet the performance they wanted. For example, in the phase comparison, or these two phases come from the same person, I can make one in a 10 million mistake. When I say they do belong to the same person, I'm 90% correct. Believe me, in 2014, we had no idea that this would be possible. In fact, when we went from phase 1 to phase 2, we were doing so well in phase 2, they made the phase 2 metrics an order of magnitude harder. There's some people here who are involved in the Janus program. It's amazing to me, right? We did that. But when we go to DIVA, which is an action detection program, performance is not that great. Why? We don't have enough annotated data for video clips. It's hard. That's all. So when you go to phase 2, they've given us 2,200 video clips, and the government decided not to give us annotated data. This is, guys, it's up to you. Do whatever you want. We want these numbers. So when you do the calculation in terms of Amazon creditors and so on, I think I'm going to spend about $80,000 to $100,000 for annotating video thing. I think if I have the data for 40 actions, the numbers will be better. So that's all there is now. I mean, if you see optical flow, shape-from shading. In fact, I did stereo using 3-layer network in 1998. Now, recently, a couple of years ago, one of Jan LaCour's students did something like that using deeper network. So, I think it's not going away. What has happened is that everything is kind of in that space. Deep networks, and I think people have kind of stopped with 101, although I hear there are deeper networks and so forth in places. So it does not happen in vision as it does happen in computation. But we still have problem. There are drastic variations in the data and so on. It may not generalize well, right? We're surprised it generalizes this well for various, because Janus data for phase is very challenging. But it failed when you have phases from ground and then you have to match with phases collected by UAV. Number is 11%. Because I end up seeing mostly called heads of these people, the volunteers. So geometry is important. So I think unless we understand, regression always had issue with geometry. Some transformations it manages, otherwise it has problems. So the next thing would be to manage the geometry and the representation. And I wouldn't call, typically we use the features, right? We train, we chop the head off and then use the features. So view this as another way of getting features, good features. As you know, in feature extraction, anything goes, as long as it works. So I tell people who are very annoyed at deep learning, I said, don't get so angry. All we are doing is we're generating task-specific features. When you do SIFT, you use SIFT for matching this, matching that, don't care. All tasks. Here, just get features that are good for face matching. Don't use it for others. And then complain it doesn't work. Start again. You have to, get a lot of data, annotate it, and train a deep network. I tell you, it's giving good numbers. So in some sense, it has simplified. But what I worry 10 years from now, all vision students will only know PyTorch. That bothers me, right? Well, it's like what happened in India, in the 80s, everybody became IT. Civil engineering, IT. Chemical, everybody became IT. So I said after a few years, nobody will know how to build a bridge. Because all the civil engineers were sitting in the computer and they're coding, and you can't build a bridge with the computer. You got to pour concrete, put steel and bolt and all that stuff. So we are generating a unidimensional, one-dimensional talent. But you can say it's an old professor who's complaining about something. It's okay. But study as much as you can. Deep learning is good. It's work, as I said, something you do for your paying bills and something you do for the soul. So learn manifolds. There's a beautiful books on differential geometry. Don't give up on that. Any other question? Yes, Dave.
So we have all this history, not only in computer vision, but physics and geometry and all these, laws and stuff. We always start over for, like you said, training data, train it, do well. For classification problems and stuff like that, it works well. What do you think about the future of trying to sort of bias these networks by, putting a base of physics and a base of all of the, sort of knowledge that we have about the world? Because we as humans obviously, use that type of knowledge when we do any type like action recognition, things like that. We use physics. Is that a future?
That will make it a very beautiful thing to do. So they're not. I used to give talks that if you don't have data, go with the models. If you have data, forget the models. So that was something I used to say. So I'm kind of hard now, but I agree. Motion. Motion coding itself, right? Yeah, it's still a challenge, right? And the human system does it very well. There's a lot of nice theories on that. So geometry, motion, and even external world, all of that, they all have to be. But right now, for doing all of that, you need to have proper annotations. So finally, that's where, and many agencies that have a lot of data are now very worried because they think the problem will be solved if only they are annotations. So they are in that framework, and then they're not able to get the annotations done. So it's becoming a more difficult situation for especially in defense and other spaces, right? Some defense company A, they want to solve a very hard problem, and then they hear about all this machine learning, how it's getting a 98% and this and that, and it's not clear whether that, for them to do that, there should be an equivalent of image net in their domain, and it's not there. And the traditional methods, you know, they work, but not up to deployment. So it's kind of interesting situation. But definitely geometry, other things. We need to do mathematics, but figuring out the deep learning network is not there yet. So there are a couple of new reasons how to understand the area of deep learning and so on. So it's hard. What makes it hard? Hierarchy. What makes it hard? Nonlinear. But keep working on it. Maybe this generation will take care of it. All right?
Other questions? Okay. I have a very basic one, betraying I've never taken a computer vision course.
Well, you should take one right away.
Yeah, I guess I should. But what are the Grassmannians used for? The Grassmannian manifolds?
Just to represent, because we are able to interpolate on that. Because see, what is happening
Polynomial interpolation. Polynomials of fixed degree k.
Yeah, that's right. See, the way it works is that it turns out, there was a meeting I was at, and I said, why are we just only using these few things, Steffel, Grassmannian, because equations are defined for them.
Yeah.
And here there was a match because the PCA subspace thing matches onto that. So it's a rare thing, but it worked out well. Because empirical manifolds are hard to, we can do experiments with it, just even define geodesic existence and so on is becoming a very messy operation. So we just go with, for example, when we do linear dynamical systems and if there are orthonormal matrices, and if you want to find the distances between them to decide whether one system is closer to the other system, then you can use the geodesic as a better metric, right? You can also use the distance between Rama parameters, but it's better to use when there is inherent geometry in the features, it's good to put it in that space and find the similarity measurement, that's all.
Okay. All right, anyone else? Okay, let us thank the speaker. There are refreshments in back, and otherwise people will go generally upstairs. Okay.